Hey guys, hope everybody's doing okay. What we're going to do today is continue with our unit on kinetics, and we're going to talk about something called reaction mechanisms. So we talked about reaction mechanisms a little bit in our thermodynamics unit, and we looked at how we figured out the overall entropy change or enthalpy change or even a Gibbs free energy change for a series of reactions, a reaction mechanism. We're going to look at those again today, and we're going to see how we could apply some information about kinetics to those reaction mechanisms. So the first thing we need to talk about is some terminology here, which is the order of a chemical reaction. So you guys had a lesson already on writing rate laws, and what we have to do is take a look at that rate law and figure out what the exponents are in that rate law and add them up. So the reaction order is equal to the sum of the exponents in the rate law. So I'm going to have a couple rate laws on the screen here, and we're going to take a look at what the reaction order is going to be for those. So if I have a rate law that says rate equals K times the concentration of NO, that is going to be simply a first order chemical reaction. Okay, so my exponent here is clearly a 1. All right, we don't worry about the rate constant K because we're just focusing on the items in our chemical reaction that are in our rate law and what the exponents are on those. So the next one here, we have rate equals K times NO2 times O3, and the exponent on both of those is 1, so this is going to be a second order rate law because you add up each of those exponents. 1 plus 1 is obviously 2. Here's another example of a second order rate law because we have K times NO squared. So obviously our exponent is 2, and that's the only exponent we have there, so add them up, we have a second order rate law. Last one is rate equals K times NO squared times O2, and that is going to give us a third order rate law. All right, so pretty easy stuff here. It's actually very rare to have a third order chemical reaction because if you think about it, what needs to happen for this to occur is you need to have 2 molecules of NO and 1 molecule of O2. All 3 of those molecules need to collide at the same time, basically, with the same amount of, with the required amount of energy, right, and in the proper orientation. So we may or may not have had a lesson on collision theory already. And if we did, we know a little bit about that. And if we didn't, then we'll learn about that a little bit more later. But to have effective collisions, you need to have correct energy amounts. You need to have the correct orientation as well. So it's very hard for 3 of those molecules to do that with the required energy and in the proper orientation. So second order reactions are a little more common as our first order and something actually called a zero order, which I'll write up here. So rate is equal to just K, and that is a 0 order. All right. There are no concentrations in that rate law, so there are no exponents. So rate is just equal to K, a constant, and that is a 0 order reaction. Let's take a look at those real quick. In 0 order reactions, there are no species in the rate law other than your rate constant. So the concentration does not affect the rate as long as there is some present. So in this case, I just have the generic substance A. If there is no concentration of A in the rate law, then the concentration of A doesn't really matter. So rate is just equal to K. All right. You can see the graph representation here. So we have rate versus concentration. And you can see as my concentration changes along my x-axis, the rate stays consistent. Okay, so for 0 order rate laws, the concentration doesn't matter as long as you have some concentration present. Over time, as time goes on, the concentration of your substance is going to decrease until you don't have any concentration left, right? And the reaction basically comes to completion. But that decrease in concentration over time has no impact on the rate of your chemical reaction. Okay, let's compare that to a first order reaction and the graphs that come with that. We're going to look at these a little bit more in a future lesson. But again, the top row here, that's your 0 order rate law with rate versus concentration and concentration versus time. You can see that for a first order reaction where you do have some concentration of some species in your rate law, as the concentration increases, so does your rate. Okay. And as the concentration decreases, your rate decreases. So concentration has an impact on rate of reaction for first order, second order, and third order reactions. It looks a little bit different, but for a first order reaction, the concentration will decrease over time, just like it does for 0 order. It just looks a little bit different. Okay? So how do you determine the rate law? The rate law has to be determined experimentally. So we had a lesson on this already where you're given some data and you have to determine the rate law from the data that's given to you. You can't determine the rate law just by looking at the chemical equation. You could predict what the rate law might be, but you can't come to a definitive correct rate law unless you do something experimentally. And we're going to do that in this class. We're going to do something called the iodine clock reaction, where we'll carry out a set of experiments, then we're going to determine the rate law based on the data that we collect. So it cannot be determined by the overall equation, but we can predict what it would look like from the overall equation. All right? So let's take a look at the equation we have on the screen here, which is CO plus NO2 yields CO2 plus NO. We could predict what the rate law would be based on what that equation looks like. And the prediction would be something like this. Rate equals K times concentration of CO times the concentration of NO2. Because these are my two reactants here, okay, that need to collide, right, and produce some products. So my predicted rate law is going to be this. Rate equals K times CO times NO2. But if I actually carry out this experiment and I collect data and I experimentally determine my rate law, from the experimental data, the actual rate law looks like this. So it's K times NO2 squared. So you're like, how could this be true? Like, how could this happen? Let's take a look at it. All right. In order for that to happen, in order for us to have a rate law determined experimentally coming out to K times NO2 squared, and our predicted rate law based on the chemical equation is K times CO times NO2, we're going to have something called a multi-step reaction. So that's a reaction mechanism. So we're used to seeing these in our thermodynamics unit, and we're going to see them again right now. So the explanation for why this could occur the way it does is that the reaction occurs in 2 steps, or maybe even more than 2 steps. So step 1, we're going to have NO2 plus NO2 yields NO3 plus NO. Now you're not going to be responsible for really writing these. We can predict what the reaction mechanism could look like, but you need to know there's a lot more that goes into it to figure these out. So usually you'll be given these, or you might be asked to predict some of these mechanisms, but not very often. Step 2, we're going to have CO plus NO3 yields CO2 plus NO2. And just like our thermodynamics unit, we're going to take a look at these mechanisms, and we can cancel out some items here. So we're going to cancel out NO2, because there's a reactant here and a product over here. We can also cancel out NO3 here and here. So you are going to get an overall equation of what we had earlier. We are going to have NO2 plus CO yields CO2 plus NO. And that's the same equation that we had here, our overall chemical equation. All right? So it just occurs in 2 steps. All right, and one of these steps is going to determine the rate of our chemical reaction. So let's go ahead and figure out which step that is. And I'm going to use an example here first, a more real-life analogy that we could apply to this. So if you're on the turnpike, and let's think of the days before Easy Pass, where you just fly through all the time without really slowing down. Even though if you have Easy Pass, you should slow down a little bit if you're blowing through some of those toll gates, right? Or those toll plazas. So top picture you guys have here. Cars are going down the turnpike, right? They're going down the highway, and they're going pretty fast. And then they have to get to Toll Plaza A, where they have to slow down a little bit. They have to slow down to pass through Plaza A, and then they continue on, on their journey here. So cars are slowed at Toll Plaza A, so the rate determining step is passing through A. So you can only go as fast as your slow step. That's what we have to learn here. So you could be going 70 miles an hour down the highway, but you come to that toll plaza, and if you actually have to pay it without using your Easy Pass, obviously you have to stop and give the person working there some money and proceed through. So you have to come to a stop or slow down at least to pass through. If you look at the second picture here, the cars are moving through Plaza A, looks like pretty quick, and then Toll Plaza B might be the one that's open. This is the one they're slowing down at. So they're going through Plaza A and they're slowing down at Plaza B. So step B is the rate determining step. Okay, so that's what we need to understand here. The slow step is your rate determining step. So if you look at the reaction that we had, step 1 and step 2, one of those reactions is the slower reaction, and therefore one of those reactions is our rate determining step. The rate determining step is going to determine our rate law. So we can already predict here which one that is going to be. So our first step is going to be considered our slow step here, because if you look at the rate law was K times NO2 squared. And that's what step 1, if I wrote the rate law for step 1, that's what I would be given, right? Like that's what I would write down for that step 1. Step 2 is going to be a fast step. Okay, so this is like Toll Plaza A here in that first picture, and this is Toll Plaza B in that first picture where cars were just going straight through it, going pretty quickly. All right? So you still are going to have your overall equation like we wrote before, but now we know what our fast step is and what our slow step is. So the slow step is the limiting step and thus determines the rate of our chemical reaction. Okay? We also call that our rate determining step. So make sure you write that on your note sheet. Slow step is your rate determining step, and that's where you get your rate law from. Okay? You're not getting the rate law from the overall equation. Now maybe the overall equation is your slow step, and it'll work out that way. But a lot of times when you have that multi-step reaction, one of these steps in the mechanism is going to be your slow step. That's your rate determining step. That's where you get your rate law from. Okay, so there we go. Rate expression can be written from the slow step, which is k times NO2 squared. So some terminology we need to pay attention to here. The whole process is called your reaction mechanism. All right, so you might have to write some of these definitions in, or at least the terms down. So step 1 and 2 is your reaction mechanism. Each individual step in your reaction mechanism is called an elementary step. So in this case, this one has 2 elementary steps in this reaction mechanism. Now in this case, we have something that is produced in the first step and used up in the second step. That is called an intermediate. So we need to know what that is. An intermediate is made and then used up. Okay. We're going to have something else called a catalyst, which we've learned about before. We're going to define that a little bit later on in one of our examples that we look at. So our rate law, rate equals k times NO2 squared. That whole thing is called the rate law. And within that, we have our k value, which is our rate constant. Now, depending on the order of reaction you have, 0, first, second, or third order, that rate constant is going to have a different set of units. So units are back here in full force, and you could tell a lot by what the order of reaction is based on your rate constant and the units that are attached to that rate constant. So we're going to talk about that a little bit more later. Okay, so you're allowed to use coefficients as exponents only in the elementary steps. So again, you have to figure out what your slow step is, and then write your rate law for that slow step, and that's going to be obviously your rate law for the overall chemical reaction. Okay, so you can see what the different ones look like here. Unimolecular, which is just one item involved in the chemical reaction here in our rate law. Rate equals k times A, so that's just A yields products. A plus A yields products is k times A squared. You can see the rest of them here. A plus B would be rate equals k times A times B. A plus A plus A, this is a termolecular, very rare, third order reaction. You can see that rate equals k times A cubed. If you had A plus B, it's rate equals k times A squared times B. And if you have A plus B plus C, very rare, 3 different things colliding here. For a third order rate law, you're going to have rate equals k times ABC. So obviously the exponents here are just 1s, right? So you have the exponents here as 1s, add them up, third order rate law for those. Okay, so we have first order here, we have second order here, and we have third order for those last 3. Okay, let's do a little bit of practice here. So given the following mechanism and rate law, what is the order of this reaction? So if you take a look at this example, I have my reaction mechanism off to the right, which is step 1, NO plus NO yields N2O2, and step 2, you have N2O2 plus Br2 yields 2NOBr. If you go ahead and cancel out what you can here, you could cancel out your N2O2, you're going to have your overall reaction, overall equation giving you 2NO plus Br2 yields 2NOBr. So it's telling you that the rate law, the experimental rate law here is rate equals k times NO squared. So a couple questions we want to answer about this. Number 1 says, which is the rate determining step? So the rate law, is based off of your slow step. So the rate law is based off of your rate determining step, which is that slow one. So which step, step 1 or step 2, is going to be used to figure out what that rate law is? It's going to be step 1. So if you wrote the reaction, or if you wrote the rate law for step 1 of that reaction mechanism, you would have this, rate equals k times NO squared. So which is the rate determining step? It is step 1. Okay. Question number 2, what's the intermediate? We just defined that on a previous slide. An intermediate is produced and then used up. So the intermediate is going to be N2O2. I love the next question because it says, what effect would doubling Br2 have on the reaction rate? So Br2 is here in our overall chemical equation, right? But look at your rate law. The only items that determine the rate of your chemical reaction are things that are found in the rate law. So if you look at your rate law, it's just rate equals k times NO squared. Bromine isn't found there at all. So what effect would doubling Br2 have on the reaction rate? It would have no effect. Okay, if you have to explain why, it has no effect because bromine is not found in the rate law expression. So it doesn't matter what your concentration is of bromine. It could be higher, it could be lower, you could double it, triple it, cut it in half. It's not going to make an impact on the rate of your reaction because it's not part of that slow step. The slow step is the step that determines your rate law and how fast the reaction is going to proceed. Okay, simple stuff. So let's take a look at writing some reaction mechanisms just to see how these work. Again, you're not really responsible for this, but I'm just going to go through these pretty quick. It says hydrogen gas combines with ICl in a second order reaction, so that is important right there, to form iodine and HCl. HI is believed to be an intermediate. Propose a mechanism for this reaction. So here's our overall equation, which is what we need to start with. So you need to start with an overall equation, make sure it's balanced. You have H2 plus 2 ICl yields I2 plus 2 HCl. Now if you look at this, if you wrote the rate law for this overall reaction, you're going to have rate equals K times H2 plus ICl squared. And that is going to give you a third order chemical reaction and a third order rate law. It says here, hydrogen gas combines with ICl in a second order reaction. So it tells us that this is not going to happen as is. This has to be a multi-step reaction here. Because, first of all, this would be very rare for this to occur. You'd have to have a molecule of H2 and 2 molecules of ICl colliding at the same time. Again, with the correct energy and orientation for that to happen. So that's third order, very, very rare. So let's try to propose a second order reaction based on the information that's given here. So let's start out with our first step, which is going to be H2 plus ICl yields HI. It did say that HI is an intermediate. Okay, so I have to figure out how can I get HI to be an intermediate here from my first step. So that's going to be H2, because I have it here. And then I'm not going to put plus 2 ICl because that would be the same as the overall equation. Let's just put one of them there. Of course, we could say HI is an intermediate. What's left? Well, H2 plus ICl, if you use up an H and an I to make hydrogen iodide there, you're going to have an H and a Cl left over. So that's what we end up with. Now it says HI is an intermediate, so we know if it's an intermediate, it's produced and then used up in the next step. So let's go ahead and figure out how can we get my overall equation, right? Because this has to be H2 plus 2 ICl yields I2 plus 2 HCl. Okay, so I need to make sure I end up with that. I already have the H2 taken care of. I need to have another ICl, all right? I also need to use up my HI and have that cancel out. So my next step is going to look like this. I have my intermediate here, which is produced and then used up, so it cancels out. Then I need another ICl for my overall equation. And then that's going to produce I2, because I have no choice. I need to produce it here. And then I need another HCl. So if you just do law of conservation of matter, if you have HI plus ICl yields I2, you have to end up with an H and a Cl left over to produce HCl. You can see if you bring everything down, you have H2, you have 2 ICl, you have I2, and 2 HCl. Okay, so this is going to be a second order reaction, and we need to figure out what our slow step is. And it's, it could really be step 1 or step 2, I guess, but most likely step 1. So the slow step would be here. We wrote the rate law for that. It'd be rate equals K times H2 times ICl, and that is going to be a second order rate law because the exponent on both of those is a 1. All right. Here's another example for you. You have dinitrogen monoxide decays into nitrogen and oxygen by means of a first order reaction. Propose a mechanism for this. Gives us a little bit of a hint. It says monatomic oxygen is known to be an intermediate. Start with the balanced equation. So dinitrogen monoxide, which is NO2, decays into nitrogen and oxygen. So if I take a look at my overall chemical equation and I balance it, if I were to write my rate law for this overall chemical equation, it's going to be rate equals K times N2O squared. And that is going to be a second order rate law. It does say this is a first order reaction. So I know this can't be right. It has to happen in multiple steps. It does say monatomic oxygen is an intermediate, so we can easily figure this out, I think. Let's start out with one molecule of N2O. Okay, one molecule of N2O, because I can't start out with both, or else I have my overall equation. I know that can't be it. So start with one, and then produce monatomic oxygen as an intermediate. So let's do that. And what's left? We have an N2 molecule left over. N2. Okay, so that takes care of the first step. Now the second step, I need to have an overall equation where I have 2 N2O. So I need another one. Let's add it. I need to use up my intermediate, my monatomic oxygen. So let's add that there. What am I going to get then? I have N2O plus O. I need to produce another nitrogen, okay, because I want to have 2 nitrogens produced. So I have one here. Let me produce another one. And then what's left? N2O plus O yields N2 plus what? Well, I have 2 oxygens left. Let's make it O2. There we go. looks like I have a reaction mechanism here that's going to work. My rate determining step, I really have no choice other than step 1 to be my rate determining step here. If I write the rate law for step 1, its rate equals K times N2O to the first, which is giving me a first order chemical reaction. It's my only reactant, and of course the coefficient there is 1, so that would be my exponent. So rate equals K times N2O. Okay, so again, you're not really going to have to write these, but it is good to see them and just kind of get that terminology down and see how it all applies here. This is the last one I think we're going to do here. So after watching the video, write a mechanism for ozone reacting with atomic oxygen to form elemental oxygen. So we're going to watch this video clip here, and then we're going to write out the reaction mechanism for this and analyze the different parts to it. We're going to define we're going to introduce a new term here as well and see how it applies.
The stratospheric ozone layer, so important to life on Earth, can be depleted by catalytic chemical processes. In recent years, man-made chemicals have contributed to the loss of stratospheric ozone. Among the most important of these are chlorofluorocarbons, or freons. For example, Freon 12. Chlorofluorocarbons, or CFCs, are very stable molecules in the lower atmosphere. Over a period of years, they slowly diffuse into the stratosphere. In the stratosphere, the CFCs are subjected to energetic ultraviolet rays that can cause rupture of the carbon-chlorine bond. The chlorine atoms act as a catalyst for the decomposition of ozone. Collision with an ozone molecule results in oxygen transfer, forming ClO and molecular oxygen. The ClO that is formed reacts with various species, notably atomic oxygen, to reform the chlorine atom and producing molecular oxygen. The sequence of reactions consists first of reaction of chlorine atoms with ozone, followed by the reaction of ClO with atomic oxygen. The overall reaction is just the decomposition of ozone. Atomic chlorine acts as a catalyst for the decomposition. Because the presence of CFCs in the stratosphere is capable of substantially reducing the ozone shield on which life depends, their manufacture and use has been greatly curtailed in the industrialized nations. Nevertheless, their effects on the ozone layer will remain for decades.
Okay, based on watching that video, here's our reaction mechanism for this. So we have ozone O3 plus monatomic chlorine yields O2 plus ClO. Based on what the video said, and then we're going to have our second step of the reaction mechanism. That's going to be ClO plus O yields Cl plus O2. We go ahead and cancel out what we need to here, and we're going to end up with our overall reaction of this. Okay, so we have Cl canceling out here. We have, looks like ClO canceling out there, and we're left with O3 plus O yields 2O2. Okay, let's define some different parts of this. One of them says, who's the catalyst in this reaction? So based on the information in that video, the catalyst in this case is going to be chlorine, okay, from those CFCs that are produced. So the chlorine's our catalyst, and that's different than an intermediate, even though it is still canceled out here. So let's talk about the catalyst in this case. A catalyst is something that is used up. Like in this case, it's used up in step 1. It's not here on the product side. But then we produce it in step 2. This is really, really neat because we did talk about catalysts before, and we know they speed up the rate of a chemical reaction, but something else we talked about in terms of catalysts is that they can be reused over and over and over again. The catalytic converter in your car, which is platinum and rhodium and I think one other valuable metal, that is just used over and over and over again. You don't have to like replace the catalytic converter because catalyst isn't used up. So if it's used up in the first step though, like that goes against what we're saying for catalysts, right? If it's used up, then it means we have to replace it. That's not the case because it has to be made again. So you use up the catalyst, you make the catalyst, then we could use it again. So it's really, really neat that catalysts are used and then made again. That's why we don't have to replace those. Okay? The other one is what we're familiar with already, is an intermediate. The intermediate here is produced and then used up. So they're pretty much opposites here. So the catalyst in this case is going to be ClO. It's made in the first step and used up in the second step. Okay, so catalyst is used and then made. Intermediate is made and then used. We just have to make sure we understand those. It shouldn't be too difficult to wrap your head around that because if you remember that catalysts don't need to be replaced. You need to make the catalyst by the time your reaction is over anyway, and that's what we end up having here. Catalysts aren't involved in, you're not going to see that in the overall chemical equation either. Like, that's why we would put the catalyst as like something above the yield sign like that. So notice you do have a catalyst here, which is chlorine, but it's not on the reactant or product side because it's not really a reactant or a product. It's just used to speed up that rate of reaction. So the difference between a catalyst and an intermediate is what we should have defined already. So make sure you fill it in on your note sheet. You can rewind it if you need to make sure you get that information, but we need to make sure we know the difference between those two if you're looking at a reaction mechanism. All right. To wrap all this up here, if I actually determine the rate constant for both of these, it says propose a rate law for this reaction. So I have my first chemical reaction, K equals 5.2 times 10 to the 9th. That's my rate constant for that first one. And my second step, I have a rate constant of 2.6 times 10 to the 10th. I have to figure out which one of these is my slow step because that's going to determine the rate law for that reaction. All right. So my slow step looks like it is step 1 because the rate constant is smaller. Of course, 10 to the 9th is less than 10 to the 10th. So a rate law for this reaction is going to be rate equals K times O3 times Cl, and I am good. All right. My rate law can't be my overall chemical reaction because it's a multi-step reaction, and it cannot be for the second step because the second step is fast. All right. So rate law is based on your rate determining step, which is the slow step, which in this case is step 1 of your reaction mechanism. So a couple main things to get from the lesson today. I don't think it's overall too difficult. You might have a couple pages to practice or a couple problems. I'll announce those on the roadmap or in the Edpuzzle video if this is on Edpuzzle. And then we'll go ahead and talk about this more in class next time I see you guys. All right, thanks guys.